Hey everyone, welcome back, and today let's solve Leetcode problem 1769 titled Minimum Number of Operations to Move All Balls to Each Box. So we have n boxes, and we are given a binary string boxes of length n, because that's how many boxes we have, where boxes at index I is the string 0 if that specific box is empty, or it's going to be a string 1 if it contains exactly one ball. So in one operation, we can move one ball from a box to an adjacent box, and box I is adjacent to box J if the absolute value of the difference of those two indices or boxes is equal to 1. In other words, they're basically next to each other, right? And note that after doing so, there may be more than one ball in some boxes. So we need to simply return an array answer of size n. Again, n is going to be the number of boxes that we have, where answer at index I is the minimum number of operations needed to move all the balls in the ith box, right? And each answer at index I is calculated considering the initial state of the boxes, which is very important, right? Initial basically meaning first, how we're actually given the boxes as an input. So in example 1, we have our input string boxes to be the string 110 or 110. That really means we have three different boxes, right? We have one, or rather two ones and a 0. In this case, our output is going to be of size 3 because that's the number of boxes we have. It's also the length of our input string boxes. And in this case, they're going to be 1, 1, 3 respectively. Right? Again, 1, 1, and 3 are the minimum number of operations needed to move every single box 0, box 1, and box 2 correspondingly to that specific box. And the reason why we actually have an output of 1, 1, 3, and basically we're just breaking down the answer of how we actually get it for each box at every single index I in this resulting answer output array. Basically for the first box here, or rather boxes at index 0, if you will, for that 0 indexed effect, basically, we have to move one ball from the second box to the first box in one operation. Once we move this ball back to this initial box, we'd have moved all the balls to this singular box here. That is just exactly one operation. This box is adjacent to it. We're just moving the singular ball in that specific box, and we're done. All right, it just takes one operation to actually do this. Right? Of course, an alternative way would be to move this 1 here and then move it back 2 times, but we want to return the minimum number of operations. And so that would literally just involve moving it 1 to the left to its adjacent box and putting it in the initial box, right? And that's going to be one operation. For the second box here that we see here, that is going to also have a minimum operation of 1. The reason why is because we literally just take this one or this box from the initial box and just move it to its adjacent box right here to the second one. That's also just one operation. We're just moving the first ball from the first box to the second box. Okay? And for the final box, the reason why this is 3, again, considering this specific initial input of boxes, right? The initial state of our input array boxes or input string boxes, we need 3 operations at minimum to get all these ones from the other 2 boxes into this last box, right? We only need 1 operation to get this guy over here, right? The ball from the second box, but we're going to need 2 operations to get the ball from the first box to the second box. The reason why is because we can only move it to its adjacent box. And so we take this 1 and move it here, and then we take this 1 again and move it here. That's 2 steps for the first box and 1 for the second. That's going to be a total of 3 operations to move all the ones from the first and second boxes to the third box that's minimized. Right? As you can see, we have to move 1 ball from the first box to the third box in 2 operations, and move 1 ball from the second box to the third box in 1 operation. And that's the reason why our output array is going to have a size of 3 with these specific values at every single box or index I. And for example 2, we have our input string boxes to be 0, 0, 1, 0, 1, 1. And in this case, we have an output with the same length of 6. And in this case, these are the specific minimum number of operations we need to actually get every single ball to this resulting box at that index for our resulting output array. Right? You may be thinking, okay, why is the first value or in the initial box having a value of 0, or rather, sorry, 11? Well, the reason why is because it's going to take exactly 2 operations to get this guy here. We move it once here and then once here. And then it's going to take a total of 1, 2, 3, 4 operations to get him here, and then to get this last one here to this initial box is going to take 1, 2, 3, 4, 5 operations. And so the total would be basically 11. It'd be 5 plus 4 plus 2 for that specific index, and applying that similar logic to the rest of the boxes to move all the balls from the other boxes to that specific box in the minimized number of operations, we see these values. Note that every single box is either going to have only 0 balls or 1 ball, and the resulting array is going to have the same length as our input string boxes, right? So for the constraints, we see that the length of our input string boxes is denoted as n, and n is going to be between 1 and 2000, not exceeding that value, which is relatively a pretty small input. And then boxes at index I is always either going to be a 0 or 1. It's always either going to have 0 balls or 1 ball, making kind of our cases pretty simple. So with that problem statement, constraints, and example out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is one really important observation that we can really take away from this problem statement and these examples here to really help us kind of lead to our most efficient solution? Well, that really is that for every single box or index I, basically we need to calculate the total distance of all the balls to that box, right? And a naive approach would basically just be iterating through all the boxes for every single index I, right? And that would be pretty inefficient for a lot larger inputs, like as you can see, up until 2000, right? So we don't want to do that, and we can basically use a lot more optimal or efficient of a solution by basically breaking the problem into 2 passes, right? So basically, how we're going to do this is, first of all, we're going to, again, solve this problem using kind of that 2-pass technique, with basically meaning 2 different for loops here, not nested, right? So one pass is going to go from left to right, and the other for loop basically is going to go from right to left. And basically, the way it's going to work is that during that kind of initial for loop here, where we go from left to right, basically we're going to accumulate the operations that we need to bring the balls from the left side to the current box, left to right, accumulative, and then from the right to left pass, we're basically accumulating the minimum number of operations required to actually bring the balls from the right side to that current box, right? So those are kind of the goals of the 2 different passes or for loops that we're going to have for the left and right to left iterations, right? And basically by actually combining these 2 passes, we can then efficiently compute the total operations for every single box in our input string boxes very efficiently, right? So kind of a quick high-level rundown of the variables and data structure that we're going to be using. First of all, we're going to have a variable operations, of course, to track the cumulative, to track actually the number of cumulative operations for one direction. And then we're going to have a variable balls that's simply going to track the number of balls that we encountered so far. And then an array answer, of course, like they're asking us to return, that's basically going to store the result for each box at every single index I. That's effectively what we're going to be returning at the end once we're done actually populating it, right? So with that kind of high-level rundown out of the way, let's go ahead and dive straight into the code here. So first of all, what I'm going to do is I'm actually going to grab the length of my input string boxes and simply just store it in n, like I usually do for most of my videos, right? Just for easy access when actually building our extra resulting array and actually iterating over our input string boxes. It's just really a lot easier, basically, right? And it really just helps us iterate through all the boxes a lot faster, right? Not runtime wise, but really just typing speed wise, right? And now let's actually iterate, or rather initialize the 2 variables that I was talking about before. That's going to be the number of operations we needed, and that's going to be the number of balls we've encountered so far. And of course, they're both going to be initialized to 0 because we haven't actually iterated over our input string boxes just yet, right? And to kind of reiterate what this is really going to do, basically, operations is going to keep track of the cumulative operations that we need so far up until this current iteration. And then the balls is basically going to count the number of balls that we've actually encountered so far as we actually iterate over our input string boxes, right? So now let's actually initialize our main results or output array. That's going to be the answer list, right? So I'm literally just going to call it answer, right? And that's exactly what the problem wants as well. And it's basically going to be initialized to all zeros. And for its length, of course, it's going to be the length of boxes. But keep in mind, we have n for a reason. So I'm just going to multiply that number of zeros by n, right? It's going to be an array answer of size n with all zeros initialized to it, right? And basically what this resulting answer is going to do again, it's basically going to store the minimum operations required to move all the balls to each box at every single index I, right? And of course, it's going to have the same number of indices I, or the same length as our input string boxes, right? So now let's actually have our first pass or for loop here, right? That's going to be the left to right for loop, right? So just iterating over the length of our input string boxes. So in this case, just n, because that's the number of indices or the length of the input string boxes that we initialize to, right? This is going to be the leftmost, this is going to be the iteration from the leftmost box to the rightmost box, right? Where our iterator is simply the current index I, right? And first of all, we want to set answer at index I for every single iteration to be the number of operations so far, right? And basically what this is really doing is we're basically, for every single index or box I, we're simply updating the answer at that index I with the cumulative operations that we've calculated so far, right? That we build in each iteration, right? And now we have to actually check, well, is boxes at this index, right? So is the current box at this current index, is that actually equal to 1? If it's equal to 1, then we know that it's going to contain exactly one ball, and so we want to then increment the number of balls that we've seen so far by 1, right? Very simple. We know that the current box is going to have one ball if it's equal to the string 1, and so we can increment the number of balls that we've seen so far, or the ball counter, by 1, which is stored in this integer ball, okay? And now let's actually kind of update the number of operations we need by the number of balls we've seen so far once we're done actually updating that variable. So we want to increment the number of operations needed by that ball's integer, right? And the reason why we're actually doing this is basically we're finally adding the number of balls that we've seen so far to that operations in this current iteration, because moving all of those balls one step to the right at each step or iteration is going to increase the total operations needed as a whole, right? So that's actually the end of the initial pass, right? That's going to be the left to right pass. So now let's actually initialize the right to left pass, right? Keep in mind, again, we're going to have basically two different passes here. This was the left pass, and now we're going to have the second pass, or kind of the rightmost to leftmost pass, right? So before actually starting the second pass, we first have to reset the operations and balls to 0. And that's going to make sure that the right to left pass basically starts fresh. It's going to have a completely brand new start. It's going to completely reset or ignore all the previous values of the balls and operations integers, right? So I'm just going to reset balls and operations to be 0. So operations is going to be initialized to 0, right? Because we don't want to actually keep the same values before we actually start the second pass, okay? So now let's actually start the second or right to left pass of this solution here. So we're going to basically be iterating backwards through our input string boxes. And the way we can do this in Python is basically loop through the range of n minus 1, decrementing by 1 each time, and going up until -1 exclusive, or basically 0 inclusive here. Basically, n is again the length of our input string boxes. We're starting from the last index. We're going up until the 0th index inclusive, or the negative first index exclusive, and we're decrementing by 1. We're going 1 to the left in every single iteration, right? That's exactly what these three parameters basically signify, right? We're going from the rightmost box to the leftmost box, right? And for every single iteration, we then want to increment or update our answer at this current index I by the number of operations we've seen so far, right? And once we've actually once we've done that, that basically means that for each box I, we're now adding the cumulative operations from the right to left pass to that answer at index I. And that basically combines the results of both the passes, both the left pass and the right pass as well. And now we have to then check, well, is the current box, does it still contain a ball? So if boxes at index I is still equal to a 1, well then we know it has exactly one ball, and we can just regularly increment the number of balls that we've seen so far by 1 like we regularly did. And finally, we simply have to then update our number of operations needed by that ball's value that we've seen so far, right? We're adding the number of balls that we've seen so far to operations because, again, moving all of those balls one step to the left is going to then increase the total operations, like we saw in the examples as well. Moving this here to the left would be 1 extra operation to the next or leftmost box, right? And believe it or not, that is basically the entire code. Once we're actually done with the second pass, we simply have to return the answer result, because it's going to actually store the resulting queries, or the resulting list, once we actually compute or finish off both of these passes, right? It's going to store for every single box at index I the minimum number of operations needed to move all the balls from the rest of the string boxes list or string to that specific box at index I. Right, so we're just returning that answer list. And so unless they made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this is really just about as efficient as you can get. So basically, to kind of reiterate what this code actually does as a whole, basically, we're again calculating the total operations needed to move all the balls to each box at each iteration efficiently using 2 passes considering the initial state of the input string boxes, right? And we're doing this efficiently using 2 passes. Right? So first of all, in the initial pass, from the left to rightmost pass, we're computing the operations needed to bring balls from the left side, and then in the right to left pass, we're computing the operations needed to bring balls from the right side. And then the sum of these 2 results for every single box at index I is going to give us the final resulting answer for that specific box in our answer result. So for the time complexity of this solution, really this is just going to be a simplified big O of n, where n is simply going to be, again, the length of our input string boxes, right? And the reason why is because really we're iterating through the string twice, once from the left to right and once from the right to left. And so technically this is a big O of 2 times n solution, but we don't really care about constants and coefficients in runtime and memory or space complexities. And so this is just a simplified big O of n runtime complexity on average. And for the memory complexity, this is also going to be a big O of n solution because really we're using that additional array answer memory array of size n, right? It's going to literally be this extra answer auxiliary memory data structure here that's also going to have the exact same size as our input string boxes. It's going to have length n, right? And it's going to actually store the results. And so apart from this, we're really only using a few integer variables like balls and operations and I guess n, but this is the real extra data structure that's going to use auxiliary memory, and that's the reason why we have a big O of n or linear time memory or space complexity. And so that's going to be it for today's video. If you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.